Pumping lemma for context-free languages is introduced in the previous lecture. Today we are going to see an application for pumping lemma. So the topic for today is pumping lemma for context-free languages, an application. Recall what we discussed in the previous lecture as the pumping lemma for context-free languages. It says for every context-free language L, there exists a constant k such that for all strings in the language with the length greater than or equal to that k, you can decompose that string into uvwxy like this, and the concatenation of v and x, if you take, cannot be the null string, and the length of the string vwx must be less than or equal to this constant, and for all I, u v raised to I w x raised to I y must be in the language. I hope you remember the statement of the pumping lemma, and if you have not watched the previous video, please do it before you see this video. This is the pumping lemma. Now before we look at an application, let us recollect some non-results from propositional logic. Consider the following two predicates. A predicate is a formula which evaluates to either true or false. Any formula whose value is either true or false is what is called a predicate. Now P is a predicate. What does it say? The computation of the DFA A on the input string W ends in a final state. It is a statement which can be either true or false. So that is a predicate. And Q is another predicate. What is it saying? The input string W is an element of the language accepted by the DFA A. Given this statement, it can be either true or false. So both are predicates. And we can verify that the implication P implies Q, which means if P is true, then Q must be true, is valid, is a valid implication for the above predicates P and Q. That is, if the computation of the DFA A on the input string W ends in a final state, then W is in the language. So that is true. It is also known from propositional logic that when an implication P implies Q is true and P is also true, that means in this particular case, suppose this is an valid implication and you know that P is true, that is the computation ends in a final state, then Q must be true. In this example, then the input string must be in the language. So if you have P implies Q and you know that the value of P is true, then Q must be true. Now look at the contrapositive of an implication. P implies Q is an implication, then its contrapositive is negation Q implies negation P. This is the definition of contrapositive. P implies Q, the contrapositive is negation of the RHS implies negation of the LHS. And it is a known fact from propositional logic that an implication and its contrapositive are equivalent. So they are equivalent. Whenever P implies Q is true, negation Q implies negation P must be true, and vice versa. which is a non-fact, and thus if P implies Q is a valid predicate and we can prove that negation Q is true, then we can conclude that negation P must be true. Okay, if you know that the implication P implies Q is valid and the negation of Q is true, then you can conclude that negation of P must be true. So, this is an important point which we will be using to derive an application for pumping lemma that we discussed in the previous class. Let us look at an application. Consider a predicate saying that L is a context-free language, that is P, which is a predicate because it can be either true or false. Now Q is this predicate which is nothing but the pumping lemma. You just recall the pumping lemma. It says for every context-free language L, there exists a constant k such that for any string z with length greater than or equal to k, all these four conditions are true. That is a pumping lemma. So it looks like an implication. What is it? P implies Q. Is that correct? Yes, you can verify because this is the pumping lemma. For every CFL something is true, which can be rephrased as if L is a CFL, because we are saying for every CFL, so we can say that if L is a CFL, then the following is true. That is exactly what we are saying here. P, L is a context-free language, that is if L is a context-free language, then Q is true, right? Q is the pumping lemma. You just now verify that I am stating it correctly. There exists a constant k such that for all strings in for all strings z in the language with the length greater than or equal to k, there exist strings uwxy such that all the four conditions, condition 1, 2, 3 and 4. Okay. Now look at the contrapositive. What is it? Negation Q implies negation P is the contrapositive, and hence from the previous slide we know that if we can prove that negation Q is true, that is the negation of this pumping lemma condition is true, then negation P must be true. That means L is not a context-free language is true. Okay. So our aim is to prove that negation Q is true. So you have to find negation Q. I hope you remember what we did when we discussed about application for pumping lemma in the case of regular languages. So what we said is that is also a very well known fact from propositional logic or quantified propositional logic. When you take negation, there exists becomes for all. So here it is there exists a natural number, it is for all natural numbers. And what is next? Here you say for all strings in the language. So here it becomes there exists a string in the language. Not that this is a condition on the bound variable, so you don't have to, you should not have to change it. Now what is next? Next is there exists 5 strings. So here it becomes for all strings, all these conditions are true. And finally for all natural numbers I. So you are here saying there exists a natural number I. And note that this is what you are talking about. For all these conditions on the bound variable, this formula is true is what you are saying. That is it must be in the language. So in the negation it becomes negation of that. Okay, it must not be in the language. So this is the negation of Q. Now the question is, how can we prove that negation Q is true for a language? observe that negation Q is an alternating sequence of for all and their axis, for all, their axis, for all, their axis. So as we did for regular languages, here again the proof of negation Q can be formulated as a game between you and your opponent, a demon, said that the for all cases, the red cases, is decided by your opponent because you don't have any control. It must be true for all possible cases. So assume that you have a nice opponent, he can give you or she can give you the best possible choice for her or him. So for all should be played by the opponent or demon, and their axis can be decided or played by you. So what I am telling is, given a context-free language L, there is a game induced by L. And what is this game? As defined by the negation of this Q, and for all parts needs to be handled by the demon, and their axis parts should be handled by you. And to start with step 1, it is for all, so it must be the demon to decide what is the value of K, because in the actual proof you have to do it for all possible values of K, which is difficult. So you assume that the demon will give you the right value of K if one exists. Okay, then what you do? You have to come up in this step 2 with a string in the language such that the length of the string that you are deciding must be greater than or equal to the value of K provided by the demon. So what is the third step? The demon needs to break the string Z into 5 substrings such that these two conditions are satisfied. That is, the concatenation of B and X should not give epsilon, and the length of the string VWX must be less than or equal to K. These are the only conditions that decomposition should satisfy, otherwise any decomposition. Now the final part, there exists. So you can choose a natural number as I, okay, and then the demon wins, your opponent wins, if the resulting string, when you substitute the value of I, which is given by you, is in the language. So if it is in the language, your opponent wins, because you are trying to prove that it is non-context free. So otherwise, that means this is not in the language, then you win, because based on the pumping lemma and the contrapositive, when it is not in the language, that means negation Q is true, and hence negation P must be true, that means language is non-context free. And by the formation of this game, it is true that if L is context free, then the demon has a winning strategy in the game. And whether or not the demon is going to win, that depends on how good she or he is in playing the game, but he is definitely having a winning strategy. Or equivalently, if you have a winning strategy, that means you are able to prove that it is non-context free, then the language must be non-context free. That is guaranteed. Now we can try to apply pumping lemma to prove that this language is non-context free. N number of A's followed by n number of B's followed by n number of C's is a non-context free language. We are going to prove it. So what is step 1? Demon is giving you a natural number K. You don't have any control on the demon or on your opponent, so don't assume any condition about K, which is a wrong step if you do it in the proof. Okay, it's just a natural number. And now you can give a string z such that whose length is greater than k. Suppose you give this string which is in the language and the length is 3k, so greater than or equal to k. And then the daemon should give you a decomposition satisfying these two conditions. Suppose the daemon is giving you a decomposition, you can expect daemon to give a decomposition satisfying these two conditions. Don't assume anything else. Now suppose you select the value of I as 2. This is a particular game, and now note that this is the string that you have selected. A k number of times, B k number of times, followed by C k number of times. There are many cases to consider. Note that the length of the string VWX must be less than or equal to k, which guarantees that you cannot have only A's in V, and when you are having A's in V, you cannot have C's in X is what this gives you, but you may not need that in this case. And case 1, either V or X contains both the simples A and B. Consider an example. This is the string that you have, and now suppose V contains both A and B. For instance, suppose V is AB. Now you are substituting I as 2, so you have to look at this string, and because you are considering a repetition of AB, the resulting string will look like this: AB because V square. Now see that in this string you are getting an A after a B, which is not allowed in the language, and hence in that particular case you are proving that the resulting string is not in the language. Another case, suppose both B and X contains only A's. Suppose V and X are drawn from this particular part of the string. Now you can easily see that in the resulting string, because you are taking V square and X square, you will be having more number of A's or B's than C's, because from this condition you cannot have more C's in the string X because of this restriction. So in that case also we proved that the resulting string is not in the language. Now a third case, the string V contains only A's. V is drawn from this set and X is from this set. In this case also it is easy to see that it is not in the language because the number of C's will be less in the resulting string. And similarly, you can show that for every case, when you substitute I as 2, the resulting string is not in the language, and hence you can conclude by an appeal to the pumping lemma of context-free languages that this language is non-context free. With this, we are coming to the last part of the lecture, where I am giving you an exercise problem for you to practice and understand how can you apply the contrapositive of the pumping lemma statement to prove that certain languages are non-context free. Today we looked at an application for pumping lemma, which is to prove that certain languages are non-context free. So we have formulated the pumping lemma for context-free languages in the contrapositive form as a game which you can play between you and your opponent. And the game is such that if the language is context free, then the opponent is having a winning strategy, and if she or he is good, in playing the game, definitely your opponent will win the game. Equivalently, if the language is non-context free, definitely you are having a winning strategy. But it is up to you. If you play the game well, definitely you can win. With this, we are finishing this lecture. Thank you.